Good, that the answer wouldn't be a real number, right? So at this point, we would probably say no solution based on where we are, right? We'd say, okay, well, to undo a square, we take the square root, but I can't take a square root of a negative number because that's not a real number solution. So we would go and say, okay, no solution or no real number solution, but that's not going to be the case any longer. We're now going to introduce imaginary numbers. So if a number is not real, then it has to be imaginary. And those are the two categories, real numbers versus imaginary numbers. And up until this point, we haven't worked with imaginary numbers at all. And starting today, we will. So before we would say that has no solution, but in reality, we meant it has no real number solution. It does have a solution, and the solution is imaginary. So what we're going to do is we're going to introduce the variable I. And I represents the square root of -1. So if I represents the square root of -1, what is I squared? Wouldn't I squared be the root of -1 times the root of -1, which is just? No, -1. And we're going to go to higher powers of I, just not today. So for today, we just need to know I and I squared. So I represents the square root of -1. I squared is -1. Let's say my directions are to simplify. And let's say I ask us to simplify the square root of -16. So the first thing we're going to do when we have this a negative under a square root is take out the negative. So this is going to be the same as saying the square root of -1 times the square root of 16. Do we agree that's the same thing? The root of 16 is the same as the square root of -1 times the square root of 16. And we know the square root of -1 is what? I. So now we have I root 16, but what's the square root of 16? So this becomes 4i. Do you think I want you to go through these little steps every single time? No, I don't. This was just me showing you how we got there. Okay, now I have the square root of -7. Right, we never leave the negative under the radical, so we're going to take out that negative, which is just an I, root 7. Can I simplify the square root of 7? No, so we leave it. Yes, Ariana. Oh yeah, that I just put it in just to show how I make it, but you don't have to. Yes.
So for these, like, is it like, does it matter if you put the I before or after those?
No, because multiplication is commutative.
Okay.
Yeah. So generally when it's like 4i, the I comes after. When it's a radical, it comes before, but it doesn't matter. Hey, you guys try this one. Tell me what you think is going to happen here or what you're going to get when you simplify this one. All right, who thinks they simplified it correctly? Nobody? It's not really a trick. Ariana? Yeah, exactly. So the first thing we're going to do is just take out that negative. So we pull out that I. So now we have I root 12. But then can't we simplify the square root of 12? Remember, 12 gets broken down into 4 and 3. And then we're looking for pairs because of that index. So one pair of 2's come out. So we have 2I root 3. Okay, so here we were just simplifying. Now I'm going to ask us to solve. So if I have x squared minus 5 equals 0, I look at this and I'm like, oh, okay, I have two terms. I have an x squared. My brain automatically goes to factoring because of the x squared. But then I realize, okay, well, 5 is not a perfect square. So I'm actually not going to try to factor this. Instead, I'm going to solve square root way. If we're solving by taking the square root, don't we have to isolate whatever quantity is squared? So I'm going to isolate the x squared. So I'm moving the 5 over to the other side by adding 5 on both sides. And now what's the quantity that's squared is by itself, then we square root both sides. Now remember, when we're just simplifying, we only take the positive version. But when we're solving, what do we have to account for once we take the square root? Plus minus. So this becomes plus minus square root of 5. Nothing new. We've done this before. Now we're going to do the same thing, but with a negative. So if I have x squared plus 4 equals 0, again, I look at this is not a dot because first, it's not a minus. Well, first and foremost, I can't factor this because it's not a minus. So I'm going to solve square root method. So I'm going to move that 4 to the other side. So I have x squared equals negative 4. Now, in the past, we'd be like, oh, no, can't solve this. There's no real number solution. But now that we've introduced the imaginary numbers, we can have a solution. It just won't be a real number. It will be an imaginary number. So we're going to go do the same thing. We're going to square root both sides, and same idea. Now that we're solving, we have to account for the positive negative version. And the square root of negative 4 is plus or minus 2i. You guys try this one. So we have 2x squared plus 16 equals 0. And you're solving for x. Okay, so what we should have done is we should have isolated the quantity that's squared. So I'm going to take this 2x squared plus 16. I'm subtracting the 16 over to the other side. So then we get 2x squared equals negative 16. Then I'm going to divide by 2. And I have x squared equals negative 8. Now, I know there won't be a real number solution. Is that okay? Absolutely. So I'm going to go ahead. I'm going to square root both sides. And then I'm going to get x is equal to plus or minus I root 8. Can I leave it like this? No, because I can simplify the square root of I, so I have to. So x is equal to plus or minus 2I root 2. How many people got that? Great. All right, now let's talk about adding and subtracting. Oops, sorry. Before we talk about adding and subtracting complex numbers, let's identify what a complex number is. So if I have the form a plus bi is defined as a complex number when a equals a real number, b is a real number, and I is imaginary. And I'm going to put a little star here, and I'm going to say every number can be written as a complex. So what do I mean when I say every number can be written as a complex number? Well, let's use an example. So an example would be the number 5. Clearly, number 5 is a real number, but I can write it as a complex. So remember, in order for it to be in a complex form, it has to be a plus bi, where a is a real number, b is a real number, and I is an imaginary number. So the way we would change 5 to a complex form, it would be 5 plus. Now, are there any imaginary numbers? So A is a real number, that's my 5. B has to be a real number, and then there has to be an I. Well, if B has to be a real number and it's multiplying with I, and there really are no imaginary numbers in 5, wouldn't that just be 0I? So this would be 5 plus 0I. So that's how I change a real number to write it as a complex form. Okay, let's simplify. So I want us to simplify, and then once it's in the complex form, I want us to identify A and B. So if I have -3 plus the square root of -4, do we all agree this becomes -3 plus 2i? Can I add -3 and 2i, do you think? No, we can't add them because they're not like terms, right? I is the square root of -1. And remember, if the radicands are not the same, the numbers inside the radicals, we can't add them. And I represents a radical. So I can't add these together. They're not like terms. So in this -3 plus 2i, let's identify the a and the b. Do we all agree this fits the format of a plus bi? So our a is -3. What's b? 2, you got it. Right. Now I want us to simplify -5 times the root of -8. So right off the bat, I'm taking out that I. So I have -5i root 8. But then I realize I can simplify the square root of 8. So we get -10i root 2. Now, if I wanted to write this in a plus bi form, would that -10i root 2, would that go with the a or the b or a little bit of both? What do you think? That would all go with the b since it's attached to the I. Is there an a written down right now? No. So if we wanted to write this in the complex form, it would be 0 plus -10i root 2. So our a is 0. And now our b is not just -10. What is our b? -10 root 2. It's everything with the I except for the I, right? Everything multiplied with the I except for the I. Yes. Yeah, of course. Okay, you guys try this next one. So I want you to simplify it. Then I want you to write it in complex form and identify your A and your B. 2 minus the square root of -10. So here, to simplify this, all we can do is pull out an I. So we have 2 minus I root 10. And this already fits the format of A plus BI. So our A is 2. What's our B?
Negative root.
Excellent, a negative root 10. Perfect. Okay, now let's talk about adding and subtracting complex numbers. So again, my directions are to simplify. And if I have 8 minus 9i plus 6 minus 4i. So we really treat I like any other variable. If it has an I in it, then they're like terms. If it doesn't, then they're not. So here our like terms are 8 and 6. And if we add 8 plus 6, we're going to get a 14. And then I have a negative 9i and a negative 4i, which gives us a negative 13i. So now I have 8 minus 9i minus the whole quantity of 6 minus 4i. Do you all agree we have to distribute in that negative? So when we distribute in that negative, we're going to get an 8 minus 9i minus 6 plus 4i. Now, once we get rid of those parentheses, now we're going to combine our like terms. And we're going to have an 8 and a negative 6, which gives us a positive 2. And then a negative 9i and a positive 4i gives us a negative 5i. That should be a negative 18, sorry. Root negative 18. Okay, the first thing I'm going to do here is simplify my radicals. So I have a negative 9 plus an I root 2. Since I have that negative, I'm just pulling out an I. And then I'm going to have 6 minus I root 18. But I can simplify root 18. So this is going to be negative 9 plus I root 2 plus 6 minus 3I root 2. And now we combine our like terms. So I have a negative 9 and a positive 6 gives us a negative 3. Then I have an I root 2 and a negative 3I root 2. Do we all agree this is a 1I root 2? So if I have a positive 1 and a negative 3, so 1I minus 3I is a negative 2I root 2. If those radicals were different, would I be able to add them? No. Okay, you guys try this one. All right, who thinks they have a simplified form for me? Perfect. Does anybody need to see me do this? We're done? Okay, moving on to absolute value of complex numbers. Okay, so I'm going to tell you how we find the absolute value of complex numbers, and then I'm going to explain why that is. So if I have the absolute value of a plus bi, and remember, when we're finding the absolute value of a number, like for example, what's the absolute value of -5? 5, what's the absolute value of +5? 5, right? So the absolute value, can somebody tell me what it represents? So if the absolute value of -5 is 5 and the absolute value of +5 is 5, who remembers what that represents? Charlie?
Distance of the number from zero.
Excellent. It's the distance a number is from 0 on the number line. So when we're finding the absolute value of a complex number, what we're going to have is the square root of a squared plus b squared. And I'm going to explain to you where this comes from. So since absolute value is the distance a number is from 0, let's say I have an example would be the absolute value of 2 plus 6i. And so we want to find the distance that number is from 0, but I can't be in a normal coordinate xy. We have to be in real versus imaginary. So here are my real numbers, and the vertical axis will be my imaginary numbers. And where they cross is still 0, 0. So when we have 2 plus 6i, that means 2 on the real, right? 6 on the imaginary. So I'm going 2 over on the real and up 6 on the imaginary, which is right here. So this is the point 2 plus 6i. And we want to find the distance that number is from 0. And how do we find the distance between any 2 points? Does anybody remember? We use the distance formula. And the distance between any 2 points is found by taking the square root of x2 minus x1 squared plus y2 minus y1 squared. Now, in this scenario, our x's will be our real, our y's will be our imaginary. So now we plug in. So we're using, obviously, where they cross the 0, 0, and we're using this point. So we're going to say 2 minus 0 quantity squared. And then for the imaginary, we're up 6. So we go 0, 0, but then up 6. So then it's going to be plus 6 minus 0 squared. And then we simplify. And when we come to simplify, oh no, I think it froze on me. Let me see. There we go. All right, then when we simplify this, what we end up with is 2 squared plus 6 squared. Well, let's go back to the formula I said we're going to use. I said if we're finding the absolute value of any complex number a plus bi, what we're going to do is we're going to take the square root of our a squared plus our b squared. Well, isn't that exactly what we just did? 2 squared plus 6 squared? Right? And that's why that works, because we're essentially just using the distance formula from the origin. So then if we simplify what's under the square root, we have 4 plus 36. And then we have the square root of 40, which is going to be 2 root 10. All right, so obviously we're not going to use the distance formula every time. I just wanted to show you where the formula came from. So now if I ask you, let's find the absolute value of negative 4i. The first thing we want to do is write it in a complex form. So is this 4i, is that our a or our b? The negative 4, a or b? That's our b, right? We're missing the a, so I'm going to write in 0 minus 4i. So my a is 0, my b is negative 4, not I. The I is not part of the b, just the negative 4. And to find the absolute value, it's going to be the square root of a squared plus b squared. So to find this absolute value, my a is 0, so this is 0 squared plus negative 4 squared, which is going to be the square root of 16, which is 4. Okay, you guys try this one. The absolute value of negative 3 minus 4i. So this is in a good format. This is in the a plus bi. So here we have our a is negative 3, our b is negative 4. So now we're going to take the absolute value and we're going to say the square root of negative 3 squared plus negative 4 squared. So we have the square root of 9 plus 16. And we have the square root of 25, which is 5. We good? All right. Last thing we're going to talk about today is multiplying and dividing. Okay, just to recap, I is the square root of negative 1 and I squared is negative 1. Do we agree? So if I have 6i times 4i, we're going to get 6 times 4 is 24, but I times I is what? I squared. I can't leave an I squared because what does I squared represent? Negative 1. So this becomes 24 times a negative 1, which is negative 24. All right, so here we have the negation of root of negative 6 or negative 1 times the square root of negative 6 times 5 root negative 3. I can't multiply these right now because I have to fix the negatives underneath, because if I multiply these right now, what would happen? Am I allowed to multiply if they're different radicands? I am, right? If they're different radicands, I'm allowed to multiply them. So when I multiply a -6 and a -3, I get a positive 18. What happens? It takes away my I, right? It takes away the I completely. So we don't want that. Before we multiply, we have to take care of the negatives underneath the radical. So let's put a little star here. We can't multiply until the I is pulled out. So we're going to pull out that I. So I'm going to have a -I√6 times a 5I√3. Now I can multiply. So now I'm going to have a -I times a 5I gives me a -5I squared. We'll talk about that in a minute. And then we're going to have square root of 6 times square root of 3 is the square root of 18. All right, first things first. I squared is what? -1. So -5 times a -1 is a +5. Is this my final answer, 5√18? No, why not? Because we can simplify the root of 18. So let's go ahead and simplify that, and we're going to get 15√2. All right, so somebody might be saying, well, then you didn't really need to take out that I because you got rid of the I anyway. No, if we were to have multiplied this initially, we would have gotten, without taking out the I, it would have been a -5√18, which would give us a -15√18. What was our final answer? Oh, sorry, -15√2. Our answer was +15√2, because when we multiplied those i's, that's how we got that -1. So you absolutely cannot leave that negative under the radical when you're doing operations. You have to first rectify it and then do the operation. All right, let's keep going. Okay, let's say I have 3 plus I quantity squared. Can I distribute in that exponent of 2? No, we have to FOIL this out. So I have a 3 plus I times another 3 plus I. And now we FOIL. 3 times 3 is 9. 3 times I is a 3I. I times 3 is a 3I. I times I is what? Yeah, it's an I. We could write out the I squared is an I squared. So now we're going to have 9 plus 3I plus 3I, but then we have I squared, which is a -1. We have to remember that. So now we combine our like terms. 9 minus 1 is 8. A 3I and a 3I is a 6I. You guys try this one. 3 plus I times the quantity of 2 minus 5I. Okay, who has a product for me? Same two hands, all class. Yes. Charlie, you're the third hand. Somebody else. Somebody else. I know you all multiplied this. It doesn't really count. Ira, what'd you get? There you go, 11 minus 13i. Who needs to see me do this? The hesitation was real. No? We got this? Okay, so we did adding, we did subtracting, we did multiplying. Last thing we're doing is dividing. Okay, so remind me, what does I represent? What does I represent? Not a trick question. What does I represent? Well, excellent. It's the square root of -1. Are we ever allowed to leave a radical in the denominator? Never. So are we allowed to leave I in the denominator? Never, right? We can't leave radicals in the denominator. We can't leave I in the denominator. So let's say I have 2 over I. I can't leave that. We have to rationalize this. We can't leave the I in the denominator. So what am I going to do? How do I get that I not to be a square root? Multiply it by itself. Exactly. Multiply it by itself, because an I times an I is an I squared, which is -1. So this would be 2i over -1, which is the same as -2i. Okay, let's say I have -5 over 6i. Is the 6 okay in the denominator? Yeah, because this is like, the 6 is like the coefficient. This is like 6 times the square root of -1. The 6 is fine. I just need to get rid of the I. I just need to get the square root of -1 away. So I'm not concerned with the 6. All I have to do is multiply by I. So then we end up with a -5i over what? A 6i squared. But what's I squared? -1. So this is -5i over 6 times a -1. So this is -5i over -6. But what is a double negative? Positive. Negative divided by a negative is a positive. So then we have a 5i over 6. Do you think you need to show me all those steps? The square root of 12 over the square root of -3. If I had the square root of 12 over the square root of 3, could I just make it the square root of 4? Yeah, because they both have the same index, right? Because they have the same index, I could have made this into one big fraction and divide the radicands. But I can't do that here. Why can't I do that here? It will compromise the integrity of the problem because it's not a real number, right? The square root of -3 is not a real number. So what we first have to do is fix that radical. And when we fix that radical, I have the square root of 12 over I root 3. Okay. Can I now divide the root of 12 and the root of 3? Yeah, because that negative's not in there anymore. So then this would be the square root of 4 over I. Do we agree that I stays in the denominator? And what's the square root of 4? 2. So now I have 2 over I. Can I leave it like this? No, I can't leave an I in the denominator. So we rationalize. I multiply top and bottom by I. So I get 2I over I squared. But what's I squared? -1. So we end up with a -2I. Okay, let's say I have 3 plus I over 2 minus 3I. Can I just rationalize by multiplying top and bottom by I? No, because if I multiply the numerator and the denominator by I, in the denominator, I have to distribute in that I. So then I would give an I to the 2, and I would cancel out the I with the 3. But that won't help me because now I'm adding a different I. So who remembers when we have a binomial in the denominator with a radical? What did we used to multiply by to rationalize this? Charlie?
You would have to change the sign and multiply it, so it'd be like 2 plus 3i.
You got it. We'd multiply it by its conjugate. Remember that? So if I have a 2 minus 3i, I'd have to multiply by a 2 plus 3i to the numerator and the denominator. Now, generally, when you have an a plus b and you multiply it by an a minus b, don't we get an a squared minus b squared? But that's not the scenario here, because when you square an I, what happens? You get a -1. So let's just FOIL this out to show you. When you have an a plus bi times an a minus bi, what you're going to get is an a squared plus b squared, and I'm going to show you why. An a times an a is an a squared. An a times a negative bi is a negative abi. Positive bi times a is a positive abi, and then a positive bi times a negative bi gives us a negative bi squared. The middle terms, as always, cancels when you multiply conjugates, but then you end up with a squared minus bi squared. But what's I squared? -1. So this is a squared minus b times a -1. Oops, sorry, b squared. I lost my squared here, guys, sorry. So then this becomes a squared plus b squared. Do you all see that? So when you multiply the conjugate of a complex number, you don't end up with a squared minus b squared. You end up with a squared plus b squared. So here, if we're going to get an a squared plus b squared, we're going to get a 2 squared plus a 3 squared. And in the numerator, we actually have to FOIL this one out. So 3 times 2 is 6. 3 times 3i is a 9i. I times 2 is a 2i. I times 3i is a 3i squared. So in our denominator, we have a 4 plus a 9, which is 13. In our numerator, I have a 6 plus a 9i plus a 2i minus 3. Everybody okay with where I got that -3 from? Because it's coming from the positive 3i squared. So now when we combine our like terms, we're going to have a 3 plus 11i over 13. If there were a GCF that I could pull out to simplify, would I have to? Yeah, but there isn't, so I won't. Okay, guys, we are done for today. You do have homework, but since next time I see you is our fun day, this homework will not be due until Thursday. So we are done for today.